Hello and welcome back to my Java tutorial series. As you can see, our product from last episode, which was advanced I/O streams, and we're gonna just get directly into this episode, which will be about Bitwise and Bitshift operators. Now, I probably should have showcased these in one of my first videos. I forget which one, where I went over other operators such as the unary operators and ternary operators, but this is a bit more in-depth and requires some other knowledge as well, which is why I'd saved it for now. And also, I know that I have been away for a bit, again, unfortunately, but that's mainly because there isn't much else that you might imperatively need to know about Java at this state. Because as far as I'm concerned, if you watched all of my tutorials so far, then you're just about ready to, develop your own applications and almost games and such. But the thing is, I'm not sure what you need to know, which is why I have I have several friends who are watching and learning from my tutorial series. And what got me to finally make some more videos was my friends saying, hey, how can you do this, and what does this do? And I'm like, well, I should probably make a tutorial on that. So again, if you're coding and don't know how to do something, want to know how to do something, or don't know how one thing works, then please drop a comment or message me, and I will make sure to definitely get a tutorial up about all the things that you need help with, because I'm really just focused on helping you learn how to program. So what we're doing today again is the Bitshift and the Bitwise and Bitshift operators. Now, about these, it would really help you to know binary, which I also have a tutorial about that on my channel, about numeral systems. And yeah, the second episode of that series was covering binary, and that will definitely help you today. I might be able to go do like a short little lesson on what's going on, but again, you'll probably want to do this. So the first thing is we're going to start out with the bit shift, because bit shift is a bit ambiguous in its uses. So basically, when you have a byte, whenever you have an integer even, let's just say you have an integer. Now an integer takes up 4 bytes, which is 32 bits, which is 32 zeros and ones. And we can set this integer to equal 1074. I should probably give it a name, indeed. So that is an integer. It's in decimal. It's obviously not in binary. But what we could do is do integer, the class, dot to binary string. And you do that on int1. And if you look down in the console, then we'll see the binary interpretation of this. And that's the binary interpretation. Now, obviously, there's a whole bunch of zeros to the left of that one, but it's not displaying it because, no one wants to see a whole bunch of zeros. But that is the binary version of 1074. Now, also, we can, as you saw, we can also do like a whole bunch of other things, like do 2 hex string, which is hexadecimal, then octal. Those are just different numeral systems, which I still have to get some tutorials out for the numeral systems. But yeah, I'm working on it. So now we know how to get to binary. What we could also do is declare this variable in binary itself by using 0b. Now in Java and several other programming languages, you can denote a certain numeral system you're writing in by 0 something. Like 0x means what's following it is hexadecimal, but 0b means binary. So if we wrote out what this thing was in decimal, then we got that. So that means if we just print out what byte 1 was, we should get 1074. And it's 1074. So that's how you can do binary literals. I mean, obviously you can add a whole bunch of zeros, but those won't do anything. But once you get above a byte, the primitive data type byte is all variables in Java are signed. And what that means, integers don't go 0 to a really high number. It goes negative really low number to positive really high number. That it can take up its bits. So if a byte Normally a byte of data can hold numbers 0 through 255. But since it is signed, that means it goes negative 170 something to positive 170 something. So it splits zeros in the middle. That way you can have it lets you have negative and positive numbers. And how binary denotes this is we can put basically 8 bytes here, and we'll just put that number. I believe that is 14 or 15. I'm not sure. Well, we'll put that there just for fun. So now if we print out byte 2, it'll give us an integer. Well, it'll give us a byte technically, but we'll see it as an integer, and that's equal to 77. But what happens, the leftmost byte, whether it's an integer, which happens to take up 4 bytes, or a byte, which is 1 byte, if we change that to a 1, we'll get an error, because right now, if this was positive, this is higher than 174.5, which is the bytes limit. So it's like, right now, it thinks it's an integer. So if we print it out now, if we like keep this as an integer, it'll print out something positive because it's an integer. But if it's a byte, it's above the limit. So if we cast it to byte, we'll get something negative, which is negative 51. Which is just a bit about how binary works. But since we know, we can just switch this back. Since we know how binary works a bit in Java now, we'll start with our Bitshift operator. And basically what Bitshift does is exactly what it says. It shifts everything in one direction however many times you want it to. So if we shifted byte 2 to the right, they are denoted by a double these characters, these are greater than, and the other ones are less than, which will shift it to the left. But this will shift it to the right however many times you want. And what happens, it fills in the left side whichever way you shift it. It'll if you shift it to the left, it'll insert zeros on the beginning, and if you shift it to the right, it'll be empty space since you're just reducing the size. So if you shift byte 1 to the right, we'll get a different number for certain, which will be 38. Suppose if we shift it 0, yeah, let's just do that, which is 77. So we can just shift it to the right one. But if we did string dot to it's integer dot to binary string, and we shift it to the 1, we can look at the binary string and we'll see it's exactly the same as this, except this 1 got shifted out of existence. And in fact, we can shift it over 2, and we'll see that 0 got shifted out of existence, and now it's just that number. And you can do the exact same thing and shift it to the right. So now it's 2 zeros were inserted to the right of this 1. Now if we don't print the binary string, we can actually see it's a whole different number because it shifts the bytes, then converts it to an integer that me and you can see. So what this is actually useful for really depends on you, because what the equivalent of this is, if you shift it to the left, it's equivalent to multiplying it by 2 to the power of this number right here. So 2 to the power of 2 is 4. So that means shifting byte 2 to the left twice is equivalent to multiplying byte 2 by 4. So if I just show a normal thing, so these should be the exact same number, 308, 308. Now, shifting it to the right, if you get an idea, it's dividing by 2 to the power of this number. So that's equivalent to dividing it, except, well, yeah, it takes the lowest integer. So if we print these out, they're both 19 and 19. So basically, if we got a more friendly number, let's not use binary literals right now. Let's do something nice. 32. 32 is an excellent number. 64 is even better, but let's go with 32. So if we print this out, it's 8. And that's divided evenly. It doesn't give you any decimals. So if we change this to like 35, it won't give us any decimals because right now it's a byte. So bytes don't include decimals. If byte 2 was a float, we would be getting decimals right now, especially with the byte structure of floats, which is weird, and we don't want to get into that. You can look that up later. It's not that important. But either way, it's going to be the exact same thing. So, maybe we get to here. So that's 2 to the power of 4, which is 16. So if we divide that by 16, then we set this to something like 156. Is it too big? Yeah, it's too big. Let's just do 112. We wanted an odd number, 115. Making up our minds. So that's 7 and 7. Yeah. So it's basically the exact same thing. It's just a little less obvious, and it might be more compact, I mean to say. So instead of dividing by some huge number like 1048, I mean 2048, you can divide by something like, what number is this? Might be 10. I'm going to go with 12 and see if it's the same. Oh, it's going to be 0 either way. So if we set this to an integer and set it to, it's not binary, but it's a big number. Okay, no, this has to be 11. But wait, no, it might have to be 13. Oh, no, 11. Yeah. So instead of dividing by, a huge number, you can just bit shift to the left or the right. There are other uses, but those are more ambiguous, and just remember this, and whenever you come across something that you think might be useful, then you can use it. I rarely ever use these, but what I have been using recently is the Bitwise operator. So let us just delete these and delete these. Now we have gone over Bitshift. Now we're going to go over Bitwise. This also operates on a binary level, so you can insert integers or whatever into it, and for convenience, well, we're going to see what this is better than. Now, imagine when I explained to you final integers, if we put this out here, public static final open equals 1, close cracked. It's basically you most of the time you use final things to denote they're basically like booleans, except they take up more than 2 values. So a door could be like completely open, completely closed, or just cracked in the middle, because there's always middle ground. And of course we could obviously assign it like 3 to 1,000 for all the different degrees of cracked open a door could be, but that's besides the point. So we know these can be used for, so if we had a variable that had an integer stored in it, it was a door, and its degree of openness is stored as an integer instead of a boolean, since it's not open or closed, it can also be cracked. Then we can check the door, its variable of its openness, against the final numbers to see how open it is. Another way to do this is bitwise. So let's just say we have the door's crackness, yeah, integer is stored in just 4 bits, which is also known as a nibble, and it's just 4 bits, 4 zeros or 1s, and or 1s. So we're just gonna say, so that means it has to be a number between 0 and 15. So if we just labeled this something like 11. 11 is good. I keep forgetting to name my variables. That's great. Now the binary form of this is 1011, if I'm correct. But let's just assume I'm correct. That means we could have another thing. So let's see, we had a nibble of information. That means we can store, that means it has 4 bits. Now imagine we could split that into 2 groups of 2 bits, and each group of 2 bits can store 4 variable, can have 4 instances. It can be 0, 0, 0, 1, 1, 0, 1, 1, and that's the number 0 through 3. And so we can have like a public static final integer unknown. I completely botched that. Unknown equals 0. So imagine it's a double door. So a double door, instead of having 2 different integers, for storing each of its doors, we could have, we'll just call this DD for double door. And we'll say that's the integer representing it, what it is. So that means to figure it out, we can do system.println DD and 3. Oh, that's not. Oh, it has to be system.out. And now these bitwise operators are just one thing. There's the ampersand. The ampersand is a bitwise AND operation. Up and down, the straight line thingy is the OR operation, and the caret is the exclusive OR operation. Now, these are different operations, obviously. But let's put this in a scope we can all recognize. So this is going to be 4 bytes. Let's just say it's 0, 0, 1, 0. So that is equivalent to the left door being closed and the right door being wait, this is the, we don't know what the left door is. Let's say the left door is closed and the right door is cracked. And again, that's the number 11. Just putting in a scope we can see. So if we do double door and 3, what happens, we're comparing it against the another number, which is equivalent to 0011. And what happens, it goes through each of these stacks up and down, so it compares 1 to 1, compares 1 to 1, it compares 0 to 1, 0 to 0, and 1 to 0. And it basically says, and, binary AND means both have to be 1, and it will return 1. Any other circumstances, it'll return 0. So that means if we demand the AND operation on this, we will get 0011. Because 1 and 1 equals 1, 1 and 1 equals 1, 0 and 0 equals 0, 1 and 0 equals 0. Because if anything is 0, it'll return 0. But if it's 1, both have to be 1 in order for it to be 1. So that means we're eliminating the values of the left door, because we don't care about the left door. Right now we're checking the right door. So if we print this out, it'll return, well, it should return 3. See, it returned 3, so that means it's opened. So then if we did the exact same method, but instead we compare it with another number, which is 12, because 12 in binary is 1100. So now if we if we do this operation, it'll get us this number, because 0 and 1 equals 0, 0 and 1 equals 0, 0 and 1 equals 0, 1 and 1 equals 1. But if we print this out, we're going to get, it just eliminates that, so it'll turn into this, which will just give us 8, which isn't within the realm. So what happens, we're actually going to take this, and we're going to Bitshift it 2 to the right, so it eliminates the 2 zeros. So now we hear, so the first door is cracked, and the right door is cracked, and the left door is closed. So we can actually do is say, we'll have 2 switches. They'll be on DD and 3. And this will be case unknown. And we'll just print out some stuff. Case unknown. Case open, case close, case cracked. I'd like to indent these, by the way. Right door is right door unknown. Then we'll have right door open, right door closed, and then right door cracked. We're going to do the exact same thing, except it'll be DD and 12, and it'll be shifted twice to the right, so we can get the left door out of it. And now we can just replace all the rights with left. So that's a compact way. So now we know right door is... Why did I do that twice? Left door is closed, left door is cracked. I disagree. Don't know how I got both of those. Oh, I see. With switch statements, you always have to add break. Because what happens, when it gets a certain case, it'll continue along all the other cases, unless you break it. So now we can try that again. Right door is cracked and the left door is closed. So that's a simple way to store multiple variables in a small amount of data. Now these are obviously, I mean, it's a byte. And if we assign it to integer, we'd be taking up 4 times as much memory. 4 times as much binary memory. A lot more times more, like 32 or 64 times as much integer memory. Which is a lot. So that's why we use bytes instead. So whenever you're like going through a method that has run a lot, you really want to be conservative with memory and use bytes and shorts instead of integers and longs, and floats instead of doubles and such. Which is what we just did here. I mean, you could have stored this in an integer. You could have stored this in 2 separate integers and checked each one against these things, or you could store it in 1 byte. And in fact, this is still half a byte. It's a nibble. You could have stored it in a whole byte. But instead, we stored it in here. And this is a small way to figure out, and we can obviously change it. Let's see, we're having a party. And both doors are open. You see, both doors are open. It's a party. And that's the AND operator to determine values. You can also do the OR operator. So let's delete this. This episode's probably getting a bit long, but hey, teaching you stuff. So this time, let's say you're getting something. You just got something from a variable, and it equals 11. We really like 11 right now. And you say, we'll have an external boolean. We'll just say, yeah, we'll just have that boolean. And we'll say, if is on, we'll just say get equals get or get or for. And eitherwise, and if it doesn't, we'll just say get equals get and what's the opposite of this? It would be -5. So that means we're just gonna make this easy. Do get, and we'll just use the binary again, so I can easily explain what the hell is going on. Now, what happens with OR is that and both have to be 1 in order for it to be 1. With OR, anything can be 1, and it'll be 1. So that means if we're checking against 4, it means this. That means this will be equal. So 1 and 0, 1 or 0 equals 1. 1 or 0 equals 1. 1 or 0, 1 or 0 equals 1. So that means we'll get this as an answer. So if we did this right now, it'll return 15. It'll return that because we printed it out. Now -5. Whenever you make a number negative, it's the 2's complement of that variable. And again, I explained 2's complement in my numeral systems binary tutorial. But you can also apply 2's complement. Like if we wanted to apply 2's we were trying to apply 2's complement to 4. So in order to do that, there's another variable, which is the tilde sign. We'll say integer 2's complement, just a random thing, would be equal to tilde will invert the bytes. It'll turn every 0 to a 1 and every 1 to a 0. So we do that to 4. We invert 4, and then we add 1. And that's applying 2's complement in Java. And that would equal -5. So we'll just copy this, and we'll just print out TCP. And that should be, shouldn't be -4. Well, no, if we take that, that inverts the byte pattern. Then adding 1 makes it 2's complement. Yeah, it inverts the byte pattern. Yeah. Basically what we're trying to do is, this is and everything except for 4. So what we were trying to get with the and there is 1011, which means it'll be exactly the same as it was before. I mean, again, even with that, there'll be a whole bunch of ones preceding that, but we don't care about that because since it's 0 and 1, all of those will be 0 since it's an AND operator. So we just want it to be the exact invert the byte pattern of 4, so we can have the exact opposite. So basically what we're doing is we're saying, hey, we're getting a value of something. This is normally used. If you use get normally with the old check method we used before using all the AND things, this is in order to set certain things on and off, individual bits. So that means if this was the door open, we'll say, let's say, is the party on? We're going to be setting it or 15 to open all the doors. Else, let's say we want to close all the doors, which will be the inversion of 15, which we can just set as that. Which, well, that means it'll be exactly the same as it was before, I think. Well, no, because the party's on. So, well, for all the doors to be open, it needs to be 5. So that means if the party's on, well, we'd be setting it. Okay, we're getting it. I'm doing the wrong thing here, just to let you know. What we would do, we would just set get equal to 5 if we were doing this analogy, which we're not trying to do anymore, because I just realized the fault in it. But either way, you could be getting something, and if it's on, it's basically adding a binary integer if we set it back to 4. It's either adding or taking away a binary integer. So let's just say all of this is 1s except for 4. So we could say add 4, which will just add a 1 there, or we could say or the inverse of 4, which will make sure it's exactly the same as before, except no matter what, even if that was a 1, this will be 0. So it's that simple. Now if we set this to false, it'll take away the 4. See? Easy as that. Now there's also the exclusive OR operation, denoted by the caret. And I'm not going to show you any example with that, but I'm going to show you what it does. So we set this to 0, 1, 0, 1, 1, 1, 0, 1. Yeah, that's good. And we did an exclusive OR operation with 1, 0, 1, 1, 1, 0, 1, 0, which is a random string of binary. How exclusive OR works means only one of them can be 1. Well, it basically means these have to be different. The 2 bytes you're comparing have to be different, and it'll give you a 1. If they're the same, it'll give you a 0. So that's 1, 1. Since 1 and 1 are the same, it's a 0. Since 1 and 1 are the same, it's a 0. Then the rest of them are separate. So that would be the exclusive OR result of that number. And I believe that is it for today's episode. A lot of content covered. The next episode, I'll be going over abstract classes, since, you know, my friend also wanted to know about those, and those are also nice to know. I'm sorry if this episode's a long one. I'm sure it's not over half an hour yet. But either way, happy to teach you programming. Again, leave a comment if you need to know something. I'd be more than happy to help you. So, goodbye, and good luck programming.